So thank you all for coming out today and joining us at our second University of Washington public lecture in quantum science and engineering. During this lecture, the front doors will be locked, so if you need to exit, please exit from the back doors. My name is Sanskriti Joshi, and I'm a PhD student here at the University of Washington in the Electrical and Computer Engineering Department. I am also one of the student members of the ACET graduate program. It is a great pleasure and honor to welcome Professor Peter Shor here today. Professor Shor is a Morss professor of applied mathematics at MIT. He completed his BA in mathematics in Caltech in 1981 and PhD in applied mathematics at MIT in 1985. After a postdoctoral fellowship at MSRI, he joined Bell Labs, where he developed his widely known algorithm, Shor's algorithm. In 2003, he then joined MIT as a full professor in applied mathematics. His research interests are in theoretical computer science, such as algorithms, quantum computing, computational geometry, and combinatorics. He's received countless awards and distinctions, including the Gödel Prize in 1999, the Dirac Medal of the International Center for Theoretical Physics in 2017, and the Breakthrough Prize in Fundamental Physics in 2023. He is a member of the National Academy of Science and a fellow of the American Academy of Arts and Science. One of the first ways that I got involved in quantum computing was by taking a quantum information science class. In this class, we learned about many algorithms, including Shor's algorithm, and it really taught me the potential of quantum computers. This is what excited me to join this field. I'd also like to extend my gratitude to the UW Quantum X, the ACET graduate program, and IBM Quantum for sponsoring this event. Also to Professor Kai-Mei Fu from the Physics and Electrical Computer Engineering Department for building the quantum community here at UW. And this is what makes this event possible. And then also to the rest of the ACET team and our volunteers, and to everyone here joining today. Before I pass the floor to Professor Shor, I would like to welcome Dr. Jamie Garcia from IBM. Dr. Garcia is the Senior Research Manager for Quantum Applications and Software team at IBM Research. One of her interests is on the application of quantum computers to chemistry and material simulations. Please give a warm welcome to Dr. Jamie Garcia.
There we go. All right, so thanks so much for the kind introduction. I'm really excited to be here today and for this amazing event. I love seeing a packed house. This is incredible. So I won't take too much time before we move on to Peter Shor's lecture, which I know you guys are all waiting for. But I did want to at least tell you a little bit about what we're doing in IBM Quantum and what we've been focusing on these days there. I'm also, just for your awareness, we're based here on the West Coast. So I come from our Almaden lab, which is located in San Jose, California. So we're actually not that far away. And I grew up here in Seattle as a sidebar. So to level set, we talk a lot about in IBM this concept of quantum utility. So a lot of people, when they think of quantum utility, they immediately juxtapose it and confuse it with the idea of quantum advantage. Quantum utility has a little bit of a different definition. So when we talk about quantum utility, what we're talking about in this instance is really showing something that you can do with a quantum computer that you cannot do with a classical computer. So it's showing a result on a quantum computer that you couldn't get classically. In quantum advantage, when you think about that, this is a much bigger picture. This is saying that we have the best solution that we can possibly get with a quantum computer. And so really, it's not up to us, IBM, or any company to say that we've reached a quantum advantage. This is really something that we expect a field or an area or an industry to say, like, yes, this is where quantum really does bring an advantage. So we have a couple of examples of quantum utility. The first one was published here in 2023, made the cover of Nature. And in this one, we were basically doing a condensed matter experiment, so using an icing model. And we were able to show that we're able to get some results on the quantum computer that you couldn't get classically without approximations. We recently published, and I won't have time to speak of it today, but another example for a chemistry example, ground state energy calculations. So definitely check that out if you haven't seen it yet. And really we want to in order to unlock the power of quantum computers, you need to be working in a regime in which you actually do have the ability to get answers with a quantum computer that you couldn't get classically. And what that means is that, there we go, you need to be able to work at scales that you otherwise would not be able to actually achieve some of these results. So, for example, this is just a plot that basically shows that the very small examples and experiments run on quantum computers aren't going to necessarily outperform or show any unique or distinct answers compared to classical. So, for example, you can see that the equivalent of an IBM PC in 1981. This is basically the same level that everyone using our 127 qubit quantum computers were working at. So if you follow that trajectory and map it out, then you really wouldn't be able to get to any sort of scale until after 2036. And that's just really not going to work in this scenario. It's going to take too long. So we need a disruptive change in order to address this. And the field has been doing this. So basically, we've been seeing an explosion of different papers that have come out in the past even year or so since we started thinking about this. So I'm not going to go through all of them, but you can see that they vary across a wide range of different areas, including things like simulation of nature, optimization, materials science, physics, chemistry, and beyond. So you really do see it in all different areas. And the list keeps growing. So the idea here is that if you actually are able to have a quantum computer that you can test some of these ideas out, that researchers are going to start using it as a tool to explore their own ideas and see whether they can find utility for their specific areas that they're interested in. So we expect this list to continue. So we're very proud to announce, and this is one of the first times that I've actually shown this slide to an audience, that over this past year, and since we announced our Heron processors at the end of last year at our summit event, we've seen that the average number of qubits has gone much higher. So this is really kind of representing between IBM quantum systems and the power of Qiskit as the software interface and API to use the quantum systems. We're starting to see things push past this utility scale with our Heron processors. So this is really exciting that we're already starting to see this again on average. But ultimately, the full promise of quantum computing at scale is going to be required to use error correction, and that's what's going to bring us to the place that we want to be. So another paper that came out just recently, again on the cover of Nature, was publishing these LDPC codes out of IBM Quantum. And effectively, this is really helping us understand what we need to be able to do next in order to create the devices and the hardware needed to be able to run these codes. And so in this particular instance, there's an order of 6 connectivity between the different qubits, and you need different types of couplers to be built to be able to actualize this. So currently what we're doing is basically leveraging this LDPC code, thinking about the hardware and the connectivity that we need between the qubits to realize error correction, and then building out what we need to in terms of the couplers to be able to connect the qubits in the right way in our future devices. So this is really, building out our quantum roadmap then. So this is there's a lot of information on here. I think that one of the things that you can look at is this bottom line in the top part of the roadmap, the black. And basically what we're showing is that we're being able to run circuits of larger and larger sizes over time in our publicly available systems. So looking at in 2024, a 5,000 2-qubit gate circuit, you can go up to 7,500 qubit gate, and then by 2028, we're looking at 15,000 operations. And then after that, it looks like there's a very stark change, being able to go from Flamingo, listed in 2028, to 2029, where we have our now Starling system available. And in this particular instance, you'll see that we changed the way that we discuss it. So now we're looking at 200 qubits, but those are logical qubits. And so this is where we think we're going to start being able to actually actualize some of the potential of the LDPC code and the engineering that we're doing behind the scenes on our systems. In addition to that, so those are all the systems that will be available to users to try out for their different areas and start exploring for utility. And then at the same time, behind the scenes, we're developing out all of the different pieces together so that we're going to be ready to produce Starling in 2029. And essentially, between looking at error mitigation, which is available today, an example of utility, we're able to run those on devices of today, and then combining that with the LDPC codes of tomorrow, we don't see that there's going to be any disruption or any roadblocks to being able to achieve some of these larger systems, and the team is extremely excited about that. And then finally, just to end on a note too, algorithm development continues to be absolutely critical and necessary at the same time. So as we're pushing the hardware forward and to higher and higher capabilities, we also need algorithm development to occur simultaneously so that you can envision as we're getting better at the hardware, the algorithms you're being able to run them on smaller and smaller circuit sizes, oftentimes as in concert with using classical post-processing techniques and breaking up circuits into multiple circuits, then these two at some point are going to intersect. And it's very hard to predict or even imagine when that will happen. So it's very important to be able to do both in concert and then also develop out the software so that you can use the tools to test hypotheses and actually do the research and explore scientific advances. So, and I just want to end on a quote from Peter Shor saying that there is still probably lots of other quantum algorithms to be found. And I think that that's really aspirational, and I think it's something that is going to continue driving our field forward, and looking forward to seeing what maybe all of you develop out in the next 30 years. And with that, I'll thank you and then turn it back over. Thank you very much.
Thank you, Dr. Garcia. Now, without further ado, I'd like to welcome Professor Peter Shor.
Thank you. Is the microphone working?
Yes.
Yeah. Okay. So let's see. There. Okay. So today I'm going to tell you about quantum computing, and most of this lecture will be on the historical development of quantum computing and quantum error correction, and much of the part I played with it, so maybe I should get started. Okay, so from its conception, quantum mechanics has been recognized as a strange theory, and there are lots of quotes on the internet from the founding fathers of quantum mechanics saying how strange this theory was. But if you start looking closer at these, most of these quotes are actually apocryphal. So there are quotes from Bohr, but, that say things like, that say things in nice, simple language. But Bohr never spoke in simple language. He spoke in very convoluted sentences, which was impossible to figure out exactly what he meant. And these quotes are interpretations of what he said. So the earliest quote I could actually find about this was from Richard Feynman. There we go. In 1964, and he said, don't think about how quantum mechanics actually works if you can avoid it, because then you'll go down the drain and find yourself in a blind alley from which nobody has ever escaped. So he actually didn't follow his advice, but I'm not going to explain that right now. So how is quantum mechanics strange? Well, if you look at the double slit experiment, if you send a particle through a screen with two slots in it, you observe an interference pattern. And now you can turn down the intensity of the particle beam until only, say, one electron goes through the apparatus at a time, and you still see this interference pattern. And so the electron must be interfering with itself because there's nothing else for it to interfere with. And the conclusion you can draw is that the single electron must go through both slits at once somehow. And this leads to the superposition principle, which has been, tested many times in quantum mechanics. If a quantum system can be one of two mutually distinguishable states, A and B, it can be in both of these states at once. And this funny notation, A and B, is what physicists use to distinguish a quantum state, and you can think about it, if you're a mathematician, as a column vector. So it can be in the superposition of two states, alpha A and beta B, alpha A plus beta B, and if you try to distinguish these states, so we assume that these two states were distinguishable, so there's some experiment you can do to distinguish these two states, then you see A with probability alpha squared and B with probability beta squared. And to illustrate the absurdity of the superposition principle when applied to large objects, Schrödinger asked the question, what about alpha A plus beta B when A is a live cat and B is a dead cat? Does 1 over root 2 live cat plus dead cat make any sense at all? And people are still arguing about this. But a qubit is a quantum system with two distinguishable states, like the polarization of a photon. And, quantum computers, just like classical computers, run on classical bits. Quantum computers run on quantum bits. So we need to understand quantum bits. So a state of a qubit is represented as a ket. So this is a vertically polarized photon. And polarization of a photon only has two distinguishable states, horizontal and vertical. And all other states can be represented as linear combinations of these basis vectors. So, for example, right diagonal is 1 over root 2 horizontal plus vertical. Left diagonal is 1 over root 2 horizontal minus vertical. And circular polarization is 1 over root 2 horizontal minus I times vertical. And the state of n qubits is a 2 to the n dimensional space. And this is one of the places that quantum computing gets its power. And in quantum mechanics, you can have two systems that are correlated more strongly than the classical laws of probability exists. And these are called entangled, and here is an example of one of these systems. And this is what Einstein called spooky action at a distance. If you manipulate one of these two systems, and you assume that the classical laws of probability hold, then you can conclude that if you're manipulating one of these two systems, you must have made a change in the other system, but you cannot transmit information faster than the speed of light this way. So while these two systems are really correlated, they're not correlated in any useful way. And for the first 30 years of the theory of quantum mechanics, nobody really considered using this strangeness. In 1968, Stephen Wiesner wrote a paper proposing a use for quantum strangeness, which he called conjugate coding. And he sent it to a journal, and it was rejected. And so the next thing he did, which is really not what you should do if you're a scientist, is he stuck it in a drawer for a decade. And his friend Charlie Bennett pulled it out of the drawer and sent it to a friend who ran a newsletter for theoretical computer science and got it published. Okay, so what were the problems Wiesner considered? Well, one of them was quantum money. The other one is oblivious transfer, and that protocol didn't actually work, so we'll stick with quantum money. So the problem with money is that you can make copies. Now, quantum states satisfy the no cloning theorem, which says you cannot make a copy of an unknown quantum state. So you might think this immediately will let us use quantum states for money, and this was essentially Wiesner's idea. And here's his quantum money scheme. In each bill is a sequence of quantum states in one of two complementary bases, so either vertical, horizontal, right diagonal, or left diagonal. And remember, this is a qubit, so there's only two distinguishable states, say like vertical and horizontal polarization. So by the laws of quantum mechanics, an inspiring counterfeiter cannot tell which spaces the states are paired in. And by the quantum no-cloning theorem, anyone who does not know the polarization of these states beforehand cannot copy them. So Wiesner proposed this quantum money protocol long before the no-cloning theorem was proved, but he obviously somehow knew it intuitively. So what are the difficulties with Wiesner's money? Well, you ask, how do you check it? Well, if you don't tell the merchant which polarizations should be there, you have to send the bill back to the bank to check whether it's valid. And this, of course, is completely impractical. Another possibility is you could tell the merchant some information about the polarizations, but not enough to copy the bill. But then a coalition of merchants could get together and collect enough information about the polarizations to copy them and then create counterfeit bills. So this doesn't really work either. Now, what Charlie Bennett and Gilles Brossard, who worked with him, did was they took the idea for Wiesner's quantum money and turned it into a quantum key distribution system. So key distribution is a cryptographic protocol where two people who communicate over a non-secure channel can agree on a secret key. So anytime you buy something over the internet, use a key distribution protocol to agree on a key to keep your credit card secure. And this is possible classically only if you assume that there's some computation problem that is difficult. For example, factoring. And you can show that with classical computers, it's possible to do it assuming some difficult computational problem, but it's impossible to do it unconditionally. And of course, we can't be sure that nobody is going to come up with a classical factoring algorithm tomorrow, which would break all the security on the internet. I mean, given that it hasn't happened for the last 40 years since the key distribution system was proposed, it's probably unlikely to happen tomorrow, but we don't have any absolute guarantees about this. So by thinking about Wiesner's quantum money, Charlie Bennett and Gilles Brossard came up with a quantum key distribution protocol that looked unconditionally secure and dependent only on the laws of physics. And here is a short description of BB84, which is their key distribution protocol. Alice sends Bob qubits in one of the 4 states. These are the same 4 states that Wiesner used for his quantum money. And then Bob measures in a random basis, either vertical, horizontal, or left diagonal, right diagonal. If the 2 bases they measure in agree, then they get the right answer. If they disagree, for example, here Alice prepared her state in the diagonal basis and Bob measured in the vertical horizontal basis, then he gets a random answer. So after Bob is measured, Alice and Bob tell each other what basis they used, and they keep the bits where their bases agree. And because an eavesdropper has to decide what basis to measure the qubits in before Alice and Bob announce their basis, an eavesdropper will inevitably make the wrong decision for some of these qubits, and that means that the eavesdropper cannot find the secret key. And this alerts Alice and Bob to the fact that someone is eavesdropping because now Bob's qubits don't agree with Alice's. So you can ask, what about imperfect apparatus? If Alice's and Bob's apparatus is imperfect, the straightforward proof doesn't work because errors could have come from the noise in their apparatus or from an eavesdropper, and it might be really difficult for Alice and Bob to tell the difference. So what Charlie Bennett and Gilles Brossard proposed is if sufficiently many of their qubits agree, then they do some extra work to reconcile their qubits. So they use an error correcting code. And to eliminate any small amount of information that Eve may have obtained, and there they use the hash function. And in the 1980s, Charlie Bennett gave a talk at Bell Labs on quantum key distribution, and I attended this talk. And I closed his talk with a question: can you prove that this protocol works? And I thought about the question for a while, but I decided I couldn't formulate the problem in mathematical terms that were definite enough for me to attack it. So now I want to step back a little bit and talk about a conference that happened several years before Charlie Bennett and Gilles Brassard came up with this quantum key distributions protocol. And in fact, Charlie Bennett was at this conference, although you can't see him in the picture because he was behind the camera. And he, quite possibly got the idea of thinking about this there. So Feynman's keynote address was called Simulating Physics with Computers. And in Feynman's talk, he made the following points. First, it seems exponentially hard to simulate quantum physics with classical computers. And one of the reasons for this is that the state space of a quantum system of n things is size 2 to the n, and that is just grows way too fast to simulate on a classical computer. So then he suggested maybe we need quantum computers to do this. And after that, a number of papers followed quantum. So David Deutsch wrote a paper, and then David Deutsch and Richard Jozsa wrote a paper which contained the first problem that was solvable more quickly on a quantum computer than a classical computer, but this really was not very convincing. And then Ethan Bernstein and Umesh Vazirani wrote another paper with another problem. And finally, Daniel Simon wrote a paper where he showed that there was a really convincing quantum speedup for, well, what we call Simon's problem. It was a problem that was contrived for this paper. But this paper is really where I got the idea for the discrete logarithm algorithm and the factoring algorithm. And I want to say one more thing about this. Apparently, when Dan Sanglin started working on this problem, his goal was to prove that quantum computers were not more powerful than the classical computers, but he actually ended up proving the opposite. So before I figured out the quantum factoring algorithm, I figured out the quantum discrete logarithm algorithm. So the discrete logarithm problem is given a prime p and residues, that's just numbers less than p, find an x such that g to the x is congruent to r mod p. Okay. So this is just like the ordinary logarithm problem, except you do everything mod p. And both factoring and discrete logarithm are hard problems that can be used as the basis for public key crypto systems, and they both give protocols for key distribution. And the interesting thing is that, there's not an immediate way of using one of these problems to solve the other, but any time that someone has figured out an algorithm for one, after a year or two, so people find a similar algorithm for the other problem. So these are connected somehow in some mysterious way. So what is Simon's algorithm? Simon's algorithm was to find the period of a function on the hypercube z mod 2 to the n. So I've colored the vertices of this cube, and this is essentially the function on the vertices of the cube. And you want to find the period is, and here the period is 1, 1, 0, because if you start at a point and move one space horizontally and one space into or out of the board, you get a point of the same color. So the period is 1, 1, 0 here. And finding the period of the vertices of a, say, 100-dimensional cube is essentially impossible classically. You need, I guess, 2 to the 100 or so time to take it, but you can do it relatively quickly on a quantum computer. And the secret is the use the Fourier transform. So I first figured out the discrete log for the case where p minus 1 is a smooth number, i.e. it only has small factors. And this case is the one that's solvable classically. But the quantum algorithm was so different from the classical algorithm that it encouraged me to keep on trying. And eventually I found a quantum algorithm for this. Now the point is that Fourier transforms are really good at finding periods. Simon's algorithm is solved by using the Fourier transform over the hypercube. And the discrete log is solved by using the Fourier transform over the integers mod m. So here are the two problems. I've gone over Simon's problem before. Here you have a very large torus. It's exponentially many points on a side. And you have to go 2 points to the right and 1 point up, and you find another point of the same color. So right, up, and it wraps around at the edges. Okay. So how does finding periods solve discrete logarithms? Well, what you do is you construct a table. Actually, you don't really construct the table because it's exponentially sized, but you virtually construct the table. And here you have the points from 1 to r to the p minus 2. Here you have the numbers 1 through g to the p minus 2. And you multiply these numbers mod p, and to get the entry in the table in the kth row and the jth column. Oh, sorry, jth row and the kth column. And the different values of r to the k, g to the j correspond to the colors of the dots in the picture on the previous slide. So if the period is st, then you have r to the s, g to the t equals 1, because if you go over s points and then up t points, you get to the same number you had here, and that means the number you've multiplied them by is 1, so that's r to the s, g to the t. So you get r to the s equals g to the minus t, or r is g to the minus t over s, and you can find minus t over s just by dividing mod p minus 1. So this gives us the discrete algorithm. So this, discrete logarithms reduce to finding periods. And the Fourier transform finds periods, so you need to implement the Fourier transform on a quantum computer. And at first I did this by, looking at the prime decomposition of the p minus 1, and if it's a smooth number, which means it's only divisible by small primes, you can just compose these quantum Fourier transforms over each small prime to get a Fourier transform over the large thing. But actually, you don't need that. If you can use a quantum Fourier transform over a smooth, a prime where p minus 1 is a smooth number, as long as p minus 1 is close to the smooth number. And that gives you the discrete log algorithm. And Don Coppersmith showed how to improve the Fourier transform by using ideas from the Cooley-Tukey fast Fourier transform to implement the quantum Fourier transform over z mod 2 to the n. And news of this factoring algorithm spread incredibly quickly. So after I told a friend at Bell Lab about it, and he checked it, and I told my boss about it, someone suggested that I talk about it in an informal internal seminar at Bell Labs, which was run by Henry Landau and happened every Tuesday. And oops. So I did that. Okay, that Saturday, I got a phone call from Umesh Vazirani in California, and he said, "Tell me how you can factor on a quantum computer." Now, one interesting thing about this phone call is I hadn't actually explained the factoring algorithm at the internal seminar. I'd explained the discrete log algorithm. And I didn't know the factoring algorithm when I gave the informal seminar. But, somehow the chain of telephone calls from whoever went to the seminar and explained it to someone, to Umesh Vazanri, changed discrete log to factoring. And luckily, I had figured out how to factor between when I gave the seminar and that weekend when Umesh Vazirani called me, so I just explained the factoring algorithm to him. I didn't explain that he got his information wrong. Okay, and then there was a bunch of more, more talks. I gave a last-minute invited talk at the Algorithmic Numbers Symposium, Theory Symposium in May. Umesh Vazirani gave a talk at a quantum mechanics conference at the Santa Fe Institute, also in May. And Arthur Eckert and David Joseph were, I guess, two researchers in England who had learned about my algorithm and wrote their own paper explaining it to physicists. And they gave, Arthur Eckert talked at the Atomic Physics Conference in Boulder, Colorado in August. Now, there were more, and another interesting development was Ignacio Cirac and Peter Zoller both attended Arthur Eckert's talk in August at the Atomic Physics Conference, and in November 1994, they figured out a way of implementing quantum computers, and they wrote a paper called Quantum Computation with Cold Trapped Ions. And cold trapped ions are now one of the leading methods for doing quantum computing. And there are lots of people doing ion-trapped quantum computing at University of Washington. And now Chris Monroe's ion-trapped quantum computer there are some pictures of Chris Monroe's ion-trapped quantum computer at Duke. And neutral atoms can be used in much the same way as ions. And this was first proposed in 1999, and now neutral atoms are really doing amazing things in terms of quantum computing. So one reaction to the factoring algorithm back in 1994 is this is never going to work in practice. And Rolf Landauer, who's quite eloquent, said in a paper, we have essentially returned to analog computers as foreseen by Asher Perez in remarkably perceptive comments made in 1985. And analog computers can do far more per step than digital computers, but they cannot take very many steps before the accumulated errors have derailed the computation. So the summary of his objection is that quantum computers are essentially analog, and analog computers cannot correct errors. So I thought about this problem, and eventually I came up with a solution. And the solution, in simple terms, is that just like quantum objects are both waves and particles at the same time, quantum computers are both analog computers and digital computers at the same time. And in their incarnation as analog computers, they can do amazing things that digital computers can't, but in their incarnation as digital computers, they can correct errors, which analog computers can't. So you could look back and say, how bad was the situation before we discovered quantum error correction? So to factor cryptographically important numbers, you probably need to perform at least 10 to the 9th quantum gates. And to do 10 to the 9th steps on a quantum computer, without any error correction, you need to implement each quantum gate, with any inaccuracy less than 10 to the minus 9th. And this seems virtually impossible to experimental physicists. So without quantum error correction, you cannot do very many steps on a quantum computer. So can you use error correction? Well, in the 1950s, I guess classical computers also were very noisy, but von Neumann showed that you can perform noise-free quantum computations classically using noisy gates with a modest amount of extra overhead. So you can ask, can you use the classical fault-tolerant techniques to make quantum computers error-resistant? So at first glance, it seemed that the answer was no. And the reason is the Heisenberg uncertainty principle and the no-cloning theorem. So what are the classical fault tolerance techniques? One is consistency checks. So every so often, you check that your computer is not in a state that is completely, that is clearly wrong. And these don't work all that well, either classically or quantum mechanically. You can use checkpoints, which is write down the state of the computation periodically, and if the computation goes awry after that checkpoint, just go back to the checkpoint. And if you think about it, this is cloning, because you need to take the state of your computer and then write it down. That means making a copy of it. There's massive redundancy, which is keep k copies of computation around and keep comparing them with each other. And if one of them is different, then classically you just throw away the different one. So does that work quantum mechanically? No, because if one of these copies of the computation fails, you need to recover k copies from k minus 1 copies, and this also violates the no cloning theorem. So the last thing is error correcting codes, and these look like they violate the no cloning theorem, but they actually work. So the simplest classical error correcting code is the repetition code, which has probably been known for several centuries, and you basically take each bit and repeat it many times. So what about the quantum version? You take a qubit, which is maybe a vertically polarized photon, and you create 3 vertically polarized photons, and then you take a horizontally polarized photon, and just make 3 horizontally polarized photons. So you can ask, is this a quantum cloner? And the answer is it's not, because if you have a diagonally polarized photon, which is a horizontal one plus a vertical one, it does not make 3 diagonally polarized photons. That would be this. It makes 3 horizontally polarized photons in a superposition with 3 vertically polarized photons. So it's not a quantum cloner, and in fact, it's an allowed quantum operation. So a qubit, we said, was a complex vector space. Evolution of quantum mechanics is linear. So a linear operation on a vector space is just a matrix. And there are 3 very important linear operations on qubits called the Pauli operations, and they're sigma x, which is this matrix, sigma y, which is this matrix, and sigma z, which is this matrix. And the quantum repetition code, you take 0 to 0, 0, 0, and 1 to 1, 1, 1, and this works against bit flips. So sigma x, so the bit flip is sigma x, which takes a 1 to a 0 and a 0 to a 1. And if you apply it on the second qubit of this encoded thing, it takes 0, 0, 0 to 0, 1, 0, and 1, 1, 1 to 1, 0, 1. And I want to claim that you can correct this because you can make the measurement which bit is different. And the possible answers are none, bit 1, bit 2, and bit 3. And applying a bit flip to the incorrect bit corrects the error. And how do you measure which different bit is different? Well, quantum mechanics says you can project onto one of these 4 subspaces, and this is a valid quantum measurement, and it answers the question which bit is different without, if you have a superposition of 1, 0, 0 and 0, 1, 1, it answers that the first bit is different, but it doesn't collapse a 1, 0, it keeps the superposition of 1, 0, 0 and 0, 1, 1 intact. So it keeps the computation intact while telling you what the error is. And you can come up with a simple quantum circuit that performs this measurement. So this works for superpositions of encoded zeros and ones. And what we could do is if we encode the state alpha 0 plus beta 1, which is a superposition, and you have a bit flip on the second qubit, that's this one, and you ask which bit is different, the result is bit 2 is different, but it keeps the superposition intact because the measurement gives the same answer for both elements of the superposition, which means by quantum mechanics the superposition is not destroyed, and bit 2 can now be corrected by applying a bit flip on bit 2. And this was realized by Asher Perez in his prescient 1985 paper titled Reversible Logic in Quantum Computers. Now, to make quantum computers work, you need to correct more than bit errors, because not only do you have to get the bits right, you also have to keep the elements of the superposition in phase, which is called keeping the computation coherent, which means you also need to protect against phase errors, which are the sigma z operations. And Asher Perez didn't need to worry about this, because all he was trying to do was implement reversible classical computation on a quantum computer. So you can ask, what happens when you encode something in a 3-qubit repetition code and you make a phase error? Well, that takes an encoded 0 is 0, 0, 0, and encoded 1 is 1, 1, 1. And you make a phase error on any of these 3 qubits. It takes 0, 0, 0 to 0, 0, 0, because 0 stays a 1, takes 1, 1, 1 to minus 1, 1, 1, because if you have a 1, you apply it to, change the phase on it. So you have made a phase error on the encoded qubit. So if you have a small rate of phase errors, this code makes them 3 times as likely. Okay, so there's another 3-qubit code you can think of. So the unitary transformation, which is this matrix, takes phase bit flips to phase flips and vice versa. So if you apply the Hadamard transformation to the 3 encoding qubits, what does this do to our code? Well, we get a new code, which is this. 0 gets to a superposition of all states with an even number of 1s, and 1 gets taken to a superposition of all states with an odd number of 1s. And, yeah. And a bit flip on any qubit here yields a bit flip on the logical qubit, because if you make a bit flip on something with an even number of 1s, it turns into a bit flip, turns into an odd number of 1s, and vice versa. So a bit flip on any qubit yields a bit flip on the logical qubit. So bit flips now have become 3 times as more likely, because our Hadamard transformation changed bit flips to phase flips and phase flips to bit flips. But we won't go into the details, but any single phase flip is correctable. So now we had this code that corrected bit flips, but not phase flips, made phase flips more likely. And we also have another code which corrects phase flips, but makes bit flips more likely. So are we stuck? And the answer is no, because there is this operation in information theory, encoding theory, called concatenating the codes. So what we do is we concatenate the codes to get a 9-qubit code. And what is concatenating codes? Well, first you encode a qubit using the 3-qubit code, and then you encode each of the remaining qubits using the other 3-qubit code. And now if you think about it, this code protects against both phase bit errors and bit errors. So this is the first quantum error correcting code discovered. So step 1, you encode using what coding theorists call the outer code. So you take 0 to this thing, which is the code that protected against phase flips, and 1 to this one, which again is the code that protects things against phase flips. And now you encode each of the resulting 3 qubits with a code that corrects against bit flips, and you get this code. And this code will correct any phase flip or any bit flip in any one of the 9 qubits. And the reason is that the outer code corrects the phase errors, and the inner one corrects the bit errors. And if you think about it, this will actually correct 1 bit error and 1 phase error. And that means it corrects all 3 of the Pauli matrices, because the sigma y can be thought of as simultaneous bit flip error and phase flip error. So that is a code that corrects against any of the 3 Pauli errors and any one of 9 qubits. Now we can answer the question, how did we get around the Heisenberg uncertainty principle? If you measure the error, you disturb the state of the system. Well, what we did is we constructed the codes which, assuming that the error is in some set of likely errors, we can measure the error without measuring the encoded quantum state, and now we can correct the error without disturbing the encoded quantum state. So the Heisenberg uncertainty principle doesn't apply. And this requires us to find codes where the likely errors are orthogonal, or nearly so, to the encoded state. And how about other errors? Arbitrary errors, measurements, unitary operations that aren't one of sigma x, sigma y, sigma z. And there's this beautiful theorem. If you can correct any error of all of the following 3 types, then you can fix any error restricted to 1 qubit. And the proof sketch is an arbitrary qubit error can be written as a 2x2 matrix. And 2x2 matrices can be expressed as a linear combination of the identity matrix, which is no error, sigma x, sigma y, and sigma z, which are the 3 Pauli errors. And now, when we measure the state to identify the error, it happens that we collapse the state to be either no error or one of the 3 Pauli errors. And when we measure the state, we identify the error. And now that we know the error, we can correct it. Okay. And you can ask, is this a paradox? Is information really physical? And you can ask where the qubit is when it's encoded in a quantum error-correcting code. And now, here is our qubit. There's a code which maps the qubit into 5 qubits, and any one error destroys, any one error can be corrected. So because of the no cloning theorem, there's no redundancy. There's only one copy of this qubit contained in these 5 qubits, but it can't be contained in any single one of these encoding qubits because removing them doesn't change it. So the qubit that's encoded is in some way in this 5-qubit system, but it's not in any single one of the qubits that are encoding it. Which, I mean, seems really weird, but again, quantum mechanics is really weird. So how many more minutes do I have? What?
It's been about 40 minutes, so you can wrap up now and keep talking.
Okay, I will skip ahead. And conclude with another slide which says that the world of quantum mechanics is not the world of your intuition. So we've already seen that the theory of computation is changed by quantum mechanics. You can perform computations in polynomial time that are not known to be efficiently doable on classical computers. So you can do discrete logs and factoring. Information theory is changed by quantum mechanics. For information theory, there's only one channel capacity classically, but there are different channel capacities. There's one for sending quantum information, one for sending classical information, and one for sending information when the sender and the receiver share entanglement. So, rather than just one channel capacity, you get at least 3 channel capacities, and classically, a feedback channel cannot increase channel capacity, but quantumly it can, so this beautiful theorem of classical information theory is broken by quantum information theory. And cryptography is also changed by quantum mechanics because new protocols are possible, like quantum key distribution, which, you can't do key distribution classically with no assumptions, and quantum mechanically you can. So quantum mechanics really changes things very much. And I have a poem which, you know, riffs off this thing. So I'm going to just read the poem now and conclude with that. I am the spooky action at a distance, the seething chaos that fills up empty space, the wave function collapse that you shall never witness, the living grin upon the dead cat's face. Am I a wave? Am I a particle? Am I analog or digital? The answer surely must be both or none. My laws say quarks and clocks alike show interference, that if you watch a state, it never changes, that two entangled systems act as one. I make superconductors lose all the resistance. I make the atom split, the laser gleam, and although you may be bewildered by my strangeness, I am real. You are living in a dream.
Thank you for that very interesting talk and also the great poem at the end. So before we open up for questions, awesome. So yeah, before we open up for questions, we would appreciate it if you were able to donate so we can continue sponsoring events like this in the future. So now for the questions, we have microphones on the ends of each of these aisles. So if you just come up to these microphones, you can ask your question.
Okay, thank you.
So I sort of didn't understand how when you're doing error correction, you figure out whether there was an error without butting into the uncertainty principle. Like, I feel like you would have to do a measurement, right?
Yeah, you do a measurement when you measure what the error was. But you do measure the error, and you don't measure the quantum state, which the computation is, or the state of the quantum computation. And that's because you've set up your system so that the measurement is orthogonal to the state of the computation, as long as the error is one of the likely errors. So you can make the measurement, and it doesn't disturb the state of the computation because the state of the computation is orthogonal to the error.
Okay. Can I have a follow-up? Sorry.
Yeah.
So what if there's an error that happens either by a decoherence or some weird mechanism where the state itself gets entangled with one of your error qubits, and then you try to measure the error qubit, but you collapse the state instead? And are there ways of getting around that?
Well, I mean, what you have to do is you have to argue that this is very unlikely because any error on less than, say, k qubits can be corrected. So for an error to be uncorrectable, you have to have some operation that affects more than k qubits at once. And if you keep your qubits far enough away, this seems unlikely. Now, there are problems with this because there are cosmic rays. And if you have a cosmic ray, it can create a muon, which can actually affect all of your qubits at once. So there are uncorrectable errors because these errors affect too many qubits at once. And this is one of the problems that people building quantum computers are trying very hard to avoid.
Thank you so much.
Yeah, this is just a quick question. So you skipped over a lot of slides at the end. I'm sure that the material there was very interesting. Will those slides be available online somewhere?
So this talk is essentially the same as the one I gave as a Killian lecture at MIT, and you can watch that talk if you want.
Okay, thank you.
I guess I'll just go ahead then.
can also ask them to ask their question.
Oh, yeah, there are
Oh, yeah,
questions over
okay.
there too, right?
Yeah.
Yes?
Yeah, it's just a question about the I think it was called the discrete log algorithm. Was that, I don't know, but yeah, you said you took a Fourier transform over a small prime. So I just wanted to like ask exactly what that meant, and then how small is the prime compared to R and to P?
Okay, so if you have a large prime, p minus 1, if you have a large prime p, you can look at p minus 1. That's 1 less than the large prime. And now suppose this large prime, suppose this number p minus 1 factors into a whole bunch of small primes. You can perform the Fourier transform mod p minus 1, which is what you want to do to figure out the discrete log operation, by just performing it on each of these small primes separately, and then if you perform it on each of these small primes separately, you've performed the Fourier transform mod p minus 1, as long as you put everything together properly, which is not that hard. So if p minus 1 factors into a bunch of small primes, then you can perform it fairly simply. Then you can perform the Fourier transform mod p minus 1 fairly simply. Now, if p is a prime where p minus 1 is not a smooth number, so it doesn't factor, you have to do something much more complicated. And I figured out how to deal with that case as well.
Nice.
Okay.
Hi, Peter. Thanks for the talk. I want to tap your intuition here. Since your algorithm, it seems to me there haven't been a lot of really big quantum algorithmic breakthroughs. Like, I guess you could say Grover's algorithm and maybe Kuperberg's algorithm. If you were to bet, what would you say would be the next big quantum algorithm sort of breakthrough to?
Okay, I really couldn't understand that question.
Oh.
I think the microphone is distorting the sound.
Okay, let me try again. Is this better?
What?
Is it? Apparently not. Maybe I just walk up there. Further? Okay, I'll try again. Is that better?
That's better.
Okay, let's try from here. So I'd like to try and tap your intuition here. Since your algorithm, it seems to me there haven't been a lot of really sort of big breakthroughs in quantum algorithmics, or big quantum algorithms. You could maybe say Grover, maybe Kuperberg's algorithm. But if you had to bet, what would you think might be the next sort of big set of problem, or maybe a few candidate problems that you think quantum algorithms might actually improve on classical with?
That's a very good question. I don't have a good answer. If I knew what the next problem that a quantum algorithm would solve was, I would be working on finding that algorithm.
Fair enough. Thanks.
Okay. Question from over that side?
Hi. Thank you for the great talk. I have a question about one of the later slides that you had on the information density, and pardon my ignorance, but it seemed to imply to me that like quantum computers can sort of go past like information theoretic limits, like from classical computers, like Shannon limit. Is that true, or am I just missing something?
So, so there's a Shannon limit for how much you can send over a classical channel.
Yes.
And now you can ask, well, does this apply to quantum channels? And you can't actually apply Shannon's formula directly to quantum channels because Shannon's formula asks, well, what is the entropy of the input plus the entropy of the output minus the joint entropy, and the joint entropy doesn't actually exist because the input and the output of a quantum channel can never be around at the same time. Now you can approximate this with things, but actually when you try the obvious approximation, you can do better. And there is a quantum formula for the capacity of a quantum channel, but yeah, I want to say one more thing. The channels which the classical capacity formula can be exceeded by quantum information actually are fairly unnatural channels. And for most natural channels, like, I want to say of optical fiber, which is definitely a quantum channel, the classical channel formula really applies, or at least comes close to applying.
Thank you.
Let's see, maybe we should take this side now.
Can you hear me? Am I loud enough and clear enough?
Yeah.
Excellent. Okay. So my question is this: so the 9-qubit code that you explained there seems pretty general from a mathematical at a mathematical level, but practically, do you think more advanced error correction codes are going to be more applicable, more tailored to specific types of implementations, for example, whether it's ion traps or superconducting devices, or do you think the generality can continue applying?
Okay, so actually there are different kinds of quantum codes we know about, and some of them are more useful for, say, superconducting qubits. For superconducting qubits, qubits can only really talk to their neighboring qubits. So you want a quantum error correcting code where you only need to make qubits talk to their neighboring qubits. And this condition applies to something called surface codes. So surface codes are really useful for this. On the other hand, you can do better than surface codes with other codes, like LDPC codes, and these may be better for ion trap quantum computers where you don't have this limitation that qubits can only talk to their neighbors. So, yeah, I mean, the other thing you can ask is, are there quantum error correcting codes which are specifically designed for the kind of errors you get on, superconducting qubits or on ion traps? And, it's really difficult to design codes to correct specific classes of error models. So we're stuck with general codes, but maybe general codes that have some local spatial structure in them.
Thank you. And I guess that's just a quick follow-up, and this is just more of an opinion question from you then. Do you think it would be research into error correction codes should be coupled with hardware development and basically continue along those tied streams, or would it still make sense to have error correction and hardware development, hardware research progress in parallel? And are there things that we lose from gain or lose from choosing one approach versus the other?
Yeah, well, if you look at classical error correcting codes, I don't think any of the great advances were made by looking at specific types of computers. They are types of channels. They were just, formulated for general channels, and then these, great new codes like polar codes or turbo codes were developed. And, once they're developed, they can then be specialized to specific types of channels. But trying to develop a new class of error correcting codes for a specific type of channel is really not going to get you very far. You need to come up with a class of error correcting codes first and then specialize them to channels.
Perfect. Thank you very much.
Is that better?
That's better.
Okay. So I'd like to try and tap your intuition here. Since you're algorithm, it seems to me there haven't been a lot of really sort of big breakthroughs in quantum algorithmics, or big quantum algorithms. Maybe say Grover, maybe Cooper-Brooks algorithm. But if you had to bet, what would you think might be the next sort of big set of problem or maybe candidate problems that you think quantum algorithms might actually improve on classical?
That's a very good question. I don't have a good answer. If I knew what the next algorithm next problem that quantum algorithm would solve was I would be working on finding that algorithm. Okay, question from over that side?
Thank you for the great talk. I have a question about one of the later slides that you had on the information density, and pardon my ignorance, but it seemed to imply to me that like quantum computers can sort of go past like information theoretic limits for classical computers, like Shannon limit. Is that true, or am I just missing something?
So, yeah, so there's a Shannon limit for how much you can send over a classical channel. And now you can ask, well, does this apply to quantum channels? And you can't actually apply Shannon's formula directly to quantum channels because Shannon's formula asks, well, what is the entropy of the input plus the entropy of the output minus the joint entropy, and the joint entropy doesn't actually exist because the input and the output of the quantum channel can never be around at the same time. Now you can approximate this with things, but actually when you try the obvious approximation, you can do better. And there is a formula, there is a quantum formula for the capacity of the quantum channel. But yeah, I want to say one more thing. The channels which the classical capacity formula can be exceeded by quantum information actually are fairly unnatural channels. The most natural channels, like I want to say optical fiber, which is definitely a quantum channel. The classical channel formula really applies, or at least comes close to applying.
Thank you.
Let's see, maybe we should take this side now.
Can you hear me? Am I loud enough and like clear enough?
Yep.
Excellent. Okay. So my question is this. So the non-jig code that you explained there only seems like pretty general from a mathematical level. But in practically, do you think more advanced error correction code is going to be more applicable, more tailored to specific types of implementations, for example, whether it's ion traps or superconducting devices, or do you think the generality can continue to apply?
Okay, so actually there are different kinds of quantum codes we know about, and some of them are more useful for, say, superconducting qubits. With superconducting qubits, qubits can only really talk to their neighboring qubits. So you want a quantum error corrected code where you only need to make qubits talk to their neighboring qubits. And this condition applies to something called surface codes. So surface codes are really useful for this. On the other hand, you can do better than surface codes with other codes, like LDPC codes, and these may be better for ion trap quantum computers where you don't have this limitation that qubits can only talk to their neighbors. So, yeah. The other thing you can ask is, are there quantum error corrected codes which are specific Yeah, well, if you look at classical error correcting codes, I don't think any great advances were made by looking at specific types of computers. They are types of channels. They were just, formulated for general channels, and then these, great new codes like Euler codes or turbo codes were developed. And, once they're developed, they can then be specialized to specific types of channels. But trying to develop a new class of error correcting codes for a specific type of channel is really not going to get you very far. You need to come up with a class of error correcting codes first, and then specialize them to channels.
Thank you very much.
Okay, shall I try to take a question from this side?
So you talked about how you, solved or found an algorithm to find the discrete logarithm, and then soon after found an algorithm for quantum Fourier, or not, for the quantum factoring algorithm. And I'm curious if the connection between those two, or like the figuring it out soon after one or the other, is because of some like fundamental mathematical relation between the two, or if it's they both use the quantum Fourier transform. That's it. Like what the connection between the two is like, fundamentally.
Okay, it's very mysterious. So so it's not just quantum algorithms. Classical algorithms, like the number field said, were first developed for the factoring problem, and then someone looked at the number field said, took it apart, figured out how to make it work for the discrete log problem, and now the number field is the best classical algorithm for both factoring and discrete log. But there's no mechanical way to take the factoring algorithm, and apply it to discrete log. You actually have to look at the details of the algorithm and figure out how these two problems are different. You need to figure out how to make the algorithm for factoring work on the discrete log problem. So it's a very mysterious connection that I don't understand.
So they're just kind of computationally tangent to each other, but not really mathematically related in any specific way.
Well, they're mathematically related, and they're both number theory problems.
Yeah.
But there's no specific rigorous mathematical connection between them that will let you take an algorithm for one and apply it to the other.
Thank you very much.
Okay, thank you.
So one of the questions I wrote down in advance of coming here was, how do you see quantum computing algorithms help support in a post-quantum world from quantum computing threats as quantum computing becomes more capable of essentially deconstructing post-quantum algorithms? So how do you foresee that progressing?
I didn't quite understand the question.
Sorry.
I'm asking about public key cryptography and how quantum computing will affect that?
Yes.
Yes. So, quantum computers will break most of the public key cryptography around. It's basically the foundation of secrecy over the internet. So what we need to do is we need to go into all these internet programs and replace the public key crypto systems based on factoring and discrete log with different quantum resistant public key crypto systems, which are generally based on this problem called learning by errors, or on some kind of computational lattices. And NIST, National Institute for Standards and Technology, has come up with at least 3 proposals for quantum-safe cryptography. And so what needs to be done before quantum computers actually become
Mainstream.
very prevalent is you need to go through all the internet codes and fix them. So this is going to be a problem, kind of like the Y2K problem, except we don't actually have a date that has to be done by. It's probably, the deadline is probably somewhere between 10 years from now and 30 years from now, and currently we don't have any idea which of these estimates is closer. question?
What happens at p equals 2, where p minus 1 does not have any prime factors?
Okay, so the quantum computers don't actually work for finding whether a number is even or not. So you need a different algorithm to test whether a number is even right.
It's kind of what I meant was what happens when you were doing all this with where assuming you were factorizing p minus 1.
Right.
What happens if you do that? What happens at p equals 2? Do you just not get anything? Or what?
Yes, so the algorithm breaks